All right, so we're going to be looking at similar figures here. And when we're talking about similarity, okay, similarity and we're talking about transformations in which they maintain the same shape as a pre-image, but not necessarily the same size, okay, but they maintain the same shape. Now, isometric transformations would work in this because they maintain both the shape and then they also maintain the size. So things like, well, we talked about before with reflections, rotations, and translations. But dilations, which we just talked about, those guys would preserve the shape, but they didn't necessarily maintain the size, okay? So we could enlarge the figure or we could reduce the figure, but the figures were still similar, okay? They had the same shape, okay? So when we're talking about transformations, there's a lot of different transformations we have looked at. For instance, there are transformations that do not maintain shape or size, like stretching, okay? Those that maintain similarity, which would be the same shape, like dilations, and then the isometric transformations, like we said, reflections, rotations, and translations, okay? Now, the ones that we're specifically focused on for similarity are these guys, and then dilations would be good examples of those that just maintain the shape, okay? Now, for definition of similarity here, we could say two figures are similar if one can be mapped onto the other by a reflection, rotation, translation, or a dilation. Okay, now specifically at the properties that we're going to maintain, it maintains shape, okay, and then to kind of add on to that, what we mean by maintain shape is that corresponding sides are proportional, like we talked about before with proportions, are proportional and corresponding angles are congruent. Okay, so it maintains a shape, and when we say maintains a shape, we're saying that the corresponding sides are proportional to one another. In other words, the ratios between the sides should be the same, okay? And the angles are going to be congruent, though. The angles will be the same measure. Now, we've talked about congruence before. The symbol we use for similarity looks like this. Well, notice the symbols are pretty similar here. The only main difference is we don't have the equals underneath, okay? So if we kind of think about what we talked about with congruence, that meant that they looked alike. We had the same, whoops, going back. We had the same shape, okay? And this meant that the measures were the same size, okay? Now, when we're saying they're similar, we're just saying they have the same shape. So that's why we don't include this equal sign underneath, okay? So congruence, we had the same shape and same size. This guy, we only have the same shape. Now, when it comes to writing similarity statements, it's similar to how we wrote congruent statements. Corresponding angles and corresponding sides of corresponding parts, the order matters in which we write things. So if they say triangle ABC is similar to DEF, like this image here, notice they have the same shape, but one is smaller, one is larger, okay? What we're really saying is that the angles are congruent, the angles are the same, but the sides are going to be proportional. Okay, so what we mean by the angles being congruent, corresponding parts are going to match. So A and angle D here, those guys are going to be congruent. So angle A and angle D are going to be congruent, just like it matches here, A and D. Then guess what? Angle B and angle E are going to be congruent, okay? So angle B over here and angle E over here are going to be congruent. and angle C and angle F are going to be congruent. They're going to have the same measures. So notice it follows that order just like when we talked about congruent statements. So corresponding angles are going to be congruent. They preserve the angle measures. However, when we're talking about the sides being proportional, what we're saying is if we were to take the sides, maybe in this case they're writing the larger side to the smaller side, okay, as a ratio. So if we take the larger length over the smaller length and write that as a ratio, those ratios between corresponding sides would be exactly the same, because all that's happening here, in order, just like when we did a dilation, all that's happening here is the corresponding parts are being multiplied by some scale factor to get to the other side, okay? So if we have AB, and DE, these guys would be corresponding sides. So the ratio between the two, if I wrote the side lengths as a fraction, DE over AB, that has to be proportional to the other side lengths. So if I take the larger side, DE over AB, that should equal the corresponding sides written as a ratio. For instance, okay, the next one they say is EF. Well, it's already blue. Let's try purple. EF and BC, okay? Or, let's see, they used FDF. Okay, so let's keep the same order here. So DF and AC, okay? So if we take the side lengths, the larger side, DE divided by AB, the side length measure EF over BC, and the corresponding side DF over AC, those ratios between the sides would all equal one another. For instance, maybe this triangle is 3 times as large as the original image here, okay? Well, that property should be maintained between each side. Those ratios should be maintained, okay? Now, with that in mind, after we kind of talked about corresponding angles being the same, and then also the proportionality between the sides, when we're talking about showing that something is similar, we could talk about being able to map through a series of transformations one image onto the other to show that they are similar, okay? Or we can use proportional sides, and we'll see that in a second, but let's just focus on this. It says establishing similarity through similarity transformation. So they're wanting to say, if I start out with this quadrilateral OBCD, okay, whoops, this guy over here, okay, if I start out with this guy, we want to go through a series of transformations to see if I can map onto OHLK. Well, notice those guys look like they have the same shape, right? So what if we did a dilation first so that they were both the same size? And that's actually what they say here. I can dilate this, double the size, remember, at our center of dilation O, and then we're multiplying by a scale factor of 2. So if I take each of those points and double them, I multiply x by 2 and y by 2, just like we looked at with dilations, then O, well, if I multiply 0 by 2 and 0 by 2, we still have 0, 0. If I multiply 0, 2 by 2, then 0 would still be 0, but 2 times 2 would be 4, okay? 2 times 2 would be 4, and 3 times 2 would be 6. 3 times 2 would be 6, and 0 times 2 would be 0. So those points would then go to O prime, B prime, C prime, and D prime, just like we see in this image here, okay? So I can dilate the figure first. Well, now things are looking pretty close, right? How can I get this image to map on to here? Well, doesn't that kind of look like a rotation? Yeah, if I rotate the image 180 degrees, that should map up so that all the points align, okay? And that's actually what they're saying here. I can rotate this 180 degrees, and we learned that to rotate 180 degrees, the mapping rule was to multiply x by a negative and y by a negative. So if I take those points here that we just found, and I multiply each x by a negative and each y by a negative, then these would be the resulting points, okay? 0 times a negative is still 0, 0 times a negative is still 0. This 4 times a negative is a negative 4, negative 4, negative 6, and negative 6, 0, okay? And that actually maps us on to this image here. Notice we have 0, 0, we have 0, negative 4, we have negative 4, negative 6, and then we have negative 6, 0. So through a couple of transformations, we show that these two images are similar because we could dilate our figure and then rotate it 180 degrees. So it maintains that shape. Now, the last few examples that I want to look at here is being able to establish that two figures are similar through proportions, okay? So examples like this and those that have missing sides. Now, these don't have any missing sides, but we can still tell if they're proportional or not. One of the easiest ways to do it is to remember that the sides are going to be proportional to one another. So if I write the shortest side length over the largest, its corresponding side, the larger length, that ratio between that side should be the same ratio as this side and this side, okay? Now, that's the way I would prefer to work through these questions, or you could do it vice versa. You could do big length over small length and big length over small length, and that's actually what they're showing on method 2. So I'm going to look at method 2 first here, okay? So the first one says I have 15, let's use a different color here. I have 15 over 5. Those two side lengths correspond. Those are the corresponding side lengths, so I can write that as a ratio. 15 over 5, the larger length over the smaller length. You could do smaller over larger. It doesn't really matter as long as you maintain that throughout. So then the next one would be 21 corresponds with 8. 21 corresponds with 8. Now, if those two are similar figures, those two ratios should be the same. They should be proportional. Well, what did we do to check for proportionality? We cross-multiplied, right? So if I take 15 times 8 and 5 times 21, if those two things turn out to be the same, then those two are proportional, those two are similar figures. Well, what's 15 times 8 going to give me? 120? What's 5 times 21? 105? Is that equal to one another? No. So those polygons are not similar, okay? They did not maintain proportionality. They are not similar. Now, the other method you could use, which is the one that I don't use quite as often, but you could use it, is you could go long to short or short to long. It doesn't really matter which, I'm going to use a different color here. It doesn't really matter between the actual figure itself. So they say, I'm going to take the shorter side 15 over the longer side 21, and that ratio between those two should be the same ratio between 5 and 8. Okay, so you could do it that way too, 15 over 21. That ratio should be the same as 5 over 8, but we're still going to end up in the same situation where they're not similar. 15 times 8 was our 120, and 21 times 5 was our 105. Okay, so either way, usually I do method 2. Okay, so I'm going to focus on method 2 on this example here. Okay, let's look at the shorter length, or actually they're using the larger length, so let's just stick with what they have. The larger length over the smaller length, okay? So in this case, we can look at the larger length of 25. This side corresponds with this side. Notice, these angles here match up with these angles here, okay? So 25 and 15 correspond here, okay? So the larger length would be 25 over 15. That ratio has to be the same ratio as the other sides, okay? So I could use the larger length of 13, and that has to correspond with 7.8, okay? That's one way we could do it. Another way we could do it is they use the example 35 and 21. So let's follow that. The larger side of 35 has to correspond with 21. Notice these angles here match up with these angles here. So 35 over 21. Now, if we cross multiply and the answers are the same for both, then those two sides, or then the ratio between the sides are proportional and the polygons would be similar. So cross multiplying, we have 25 times 21, 15 times 35. What do we get for both? 525, right? So if we get the same thing for both, that means that the sides are proportional to one another and the polygons are similar. In other words, they have the same shape, okay? Might not be the same size, but they have the same shape, okay? The side lengths are proportional, okay? Now, the other situation we can run into is, what if we're missing sides, okay? So maybe they don't tell you all the sides and you want to find X or you want to find Y. Well, it's still the same information here, okay? So this says that triangle ABC is similar to EDC. Now, if they don't tell you which part corresponds to which part, make sure you look at the angles in order to tell which angles go together, Okay, so make sure that you're checking the angles to help figure out which things go together. But in this case, they tell us which parts correspond to which part. Okay, now again, I like to use the second method, and in this case, they start out with the smaller length over the bigger length. Again, it doesn't matter if you do big to small or small to big, as long as you maintain that in your ratios. Okay, so let's take the example that we already know. We know that the smaller side is 2 corresponds with this larger side BC. Okay, so in this example here, we know that BC corresponds with DC. Okay, so we can use that in our ratio, 2/5. That's one of the properties we know. Okay, however, what we do not know is we don't know what y and x are. Well, the first one they're looking for is y. Now, which side corresponds with that? Well, this is CA. Well, isn't that going to correspond with CE, just like in our example up there? So 3 corresponds with y. So we have the smaller side 3 over the larger side y. Just make sure if you're doing small and big, you maintain that, small over big. So in this case, do I have my ratio set up? So now we're just cross multiplying. 5 times 3 is 15. 2 times y is 2y. If I divide by 2, then I get y is 7.5. So we can find a missing side length using proportionality. Same thing with finding x. Notice AB over here is going to correspond with ED. Okay, AB is going to correspond with ED. I can still use 2/5. That doesn't change. But in this case, the smaller length is x, so we put x on top, and the larger length is 8 on bottom. Cross multiplying 5 times x, and then 2 times 8, so we get 5x and 16. Divide by 5 to both sides, and we get x equals 3.2. So x is 3.2. Okay, so we can find missing side lengths using that proportionality of knowing that the sides are proportional for similar figures. Okay.